And now we continue discussing properties of eigenvalues and eigenvectors. This is part 2 of properties of eigenvalues. So let's consider a square matrix. The context in which we're working here has to do with matrices that have the same number of rows and columns. So the eigenvalue equation is something that looks like A times X. That product, it's a column vector, and that column vector equals a scalar times a vector, scalar multiplication, and that scalar is denoted as lambda, and we can use here the notation X. As we had mentioned before, it's okay to write something like A times X equals to lambda X, but we can use a different notation. A times V equals lambda V, or we can use A times U equals alpha U, right? So the important thing is that we're saying that a matrix vector product is exactly equal to a multiple, specifically a scalar multiple of that same vector. So in that context, we consider the following. Suppose we have a square matrix, then, and this is one important theorem because we have here an if and only if, right? So let's get, I'm pretty sure well, I don't know if I'm pretty sure, but in case, if you're familiar, good. If you're not, so this is the notation when we have a single arrow, well, an arrow of this type, this means implies, right? So this is the formality in formal logic. And if we have, so that would be something that say P implies Q, for example. But you could also have that Q implies P, right? And so in those circumstances, when both of them, if you have that P implies Q and Q implies P, then you would write something like P double arrow Q. And so this double arrow, another way of saying those words that appear here, if and only if, sometimes is by saying, by writing IFF, or by writing a double arrow. P double arrow Q implies P if and only if Q. And so that's a way of saying in symbolic logic, you know, that a statement, you can start with P and that implies Q, but you could also start with Q and that implies P. And this is one of such theorems. A is singular if and only if lambda 0 is an eigenvalue of A. Well, and how do we write a proof for this? So first thing, there are a few ways of writing a proof, but luckily we could exploit the fact that this is an if and only if type of theorem. So we can start by writing, you know, A is singular, and let's remember what that means. That singularity, the definition of singularity, has to do with the null space of the matrix. So if that null space contains only, if this null space is a set that contains only one vector, and that vector is the trivial vector, the vector of all zeros, if this is the case, then the matrix would be, this is a case in which we say that matrix is non-singular. So if the only member of the null space is the trivial vector, the vector of zeros, then the matrix is considered non-singular. If that is not the case, if the matrix is considered singular, that means that null space, so if this is not the case, if the matrix is not non-singular, that means that is in fact singular, and singularity means that the null space is the set of vectors, I don't know, here we can write W, vectors W in Cn, such that the matrix times W equals 0, but this is the 0 in Cn also. Okay, so these are vectors that when multiplied by the matrix on the right side, that matrix vector product equals the zero vector. But this is also a solution set, right? This is a solution set of a homogeneous system. So that's a homogeneous system, right? And so these are solutions of a homogeneous system that has A as the matrix of coefficients. And that is what it means for that matrix to be singular. It means that this as a set, as a solution set, contains infinitely many of such vectors, and that these vectors may include the trivial vector, but they also include other vectors that are not they're not trivial vectors. They're not zeros. They're not vectors made of zeros in all entries. Some entries may be zeros, but not all of them. So that's what singularity is. If the matrix is singular, so the matrix is singular if and only if there exists X. And so remember this this symbol here, which looks like the letter E, is a symbol that means there is or there exists. Okay, there exists a non-trivial vector X. A non-trivial vector X, meaning that there exists a vector X which is not equal to 0, such that I'm writing you a lot of logical symbols from symbolic logic. There exists X non-trivial, there exists X not equal to 0, such that the matrix times that vector X is equal to 0. So that's what it means, that X, this is another way of saying that X is in the null space of the matrix A, and that such X is not the zero vector. Okay, so A is not singular if and only if there is a non-trivial member of the null space of the matrix, and that means that A times X equals 0. And then we have that AX equals 0 if and only if same statement we write, that exists X not equals 0, but then we're gonna rewrite this same thing we had there, AX equals 0, but now we're gonna write this. So we're gonna write this right hand side as 0 times X, okay? And I want to point out that we're writing the right hand side as 0 being here the scalar. So we're writing the 0 vector, okay? What we had written on the first if and only if, this 0 here, remember, is the 0 vector in Cn, just as we have in the definition of the null space. But we're writing that 0 vector as the multiplication of the 0 scalar times a non-trivial vector. So the shape of this vector equation is we have a square matrix times a column vector on the left side, and on the right side we have a scalar 0 times a column vector. Okay, this is how we want to think of this. And this is simply stating, this is something that states that lambda equals 0. So this, in other words, this is something that we would imply, this is something that we would articulate as lambda equals 0 is an eigenvalue of the matrix A. Okay, so this is the way in which we have written the proof of this theorem. A is singular if and only if lambda equals 0 is an eigenvalue. So we say, A singular if and only if there is a non-trivial member of the null space that is X different from 0, which satisfies that AX equals 0. And that is true if and only if that 0 on the right side of that vector equation is expressed as the scalar 0 times the non-trivial vector. But then that precisely gives us a vector equation of this type, right? And this is saying here you have a matrix times a vector, and here you have a scalar times the same vector. So that scalar there being, that's the key, right? And that scalar there is what allows us to say, excuse me, is what allows us to say lambda equals 0. So I do apologize for the sound effects, in case you were wondering. Yeah, that was a dog barking, and but I hope that you can bear with me. So an important thing is that lambda equals 0 and eigenvalue equals 0 implies the matrix is singular. So there is a direct connection with having a 0 eigenvalue and the null space of the matrix. And singularity is directly related to the existence of a 0 eigenvalue. So such information can be summarized on this theorem that we keep updating and updating, right? So that we have a square matrix, and all these statements are equivalent to each other. And now we have just updated this theorem by adding that indeed, if the matrix is non-zero, if the matrix is non-singular, then the eigenvalues are not 0. So having a 0 eigenvalue is an equivalence to being singular, and if the matrix is non-singular, then lambda equals 0 is not an eigenvalue of the matrix, right? So that adds to the list of equivalences of non-singular matrices, such as, you know, all the other things. So one thing to keep here in mind is that now, maybe finally, at last, this idea of having a 0 eigenvalue is now also related with the determinant equal to 0, and then with this name of the name that we denote here as singularity. So non-singular, non-zero determinant, non-zero eigenvalue, 0 eigenvalue, 0 determinant, singular matrix. Well, and for now, this is what we have to say about 0 eigenvalues and non-singular matrices. And I just want to end with a note. Again, please do accept my apologies. You heard a dog barking, and I just don't want you to think that you were crazy listening things that you were indeed listening to this little lady dog. She's 80 something, she's 13 years old, and I guess she doesn't like 0 eigenvalues, so she was barking. So please do accept my apologies, and we'll continue in the next video lecture with more on properties of eigenvalues.